Welcome fellow chemists to the fourth video on the reactions of the alkynes. As I said at the end of the previous video, I will make a nomenclature one about ketones and the ones we encountered today, but if you have other suggestions, please let me know. Today we will take a closer look at hydroboration-oxidation. As before, you should watch the previous video on the same process with the alkenes. If we have an internal alkyne, everything is the same as it was for alkenes. We have 3 molecules of alkyne for every borane, and the reaction takes place in THF. Each of the alkynes bonds to the boron, and the triple bond becomes a double bond. In the end, we have a trialkyl borane. After sodium hydroxide and hydrogen peroxide are added, the alkenes become enols, which then quickly rearrange into ketones. Since these are symmetrical alkynes, there is only one ketone produced. On the other hand, if the alkyne is asymmetrical, the mechanism is the same, but there is an equal distribution of 2 ketone products. But if borane reacts with regular alkenes, shouldn't it also react with boron-substituted alkenes? If it did, we get this weird diboron-substituted molecule. Well, it comes down to the structure of boron-substituted alkenes, which may look like this in 2D. Yes, 3D would be better, but I really don't know how to make it look nice with the coding I use here, though if I ever figure it out, I will use it. The R groups, which are methyl groups or something larger, along with the rest of the structure, prevent another borane from getting close enough to the double bond to react again, saving us all from having to remember something complicated. But all that goes out the window if the alkyne is terminal. Due to its location at the end of the molecule, there is enough room for a borane to react again. To avoid additional substitutions, a different reagent is used. If this is borane, we need to bring in some muscle. The significantly more buff dicyamyl borane can be used instead. This reagent behaves similarly, but it contains 2 bulky groups which stop another dicyamyl borane from reaching the double bond. But there is another swole doge we can use instead. This one, known simply as 9BBN, has the same effect as the other. These bulky boys prevent the unwanted reactions. Now that we can return our focus to actually adding the water, remember that the process for alkenes flipped the script on where the OH landed. This means for terminal alkynes, the OH ends up on the primary carbon, resulting in an enol. We know enols tautomerize, except we do not get a ketone when it happens here. This structure is known as an aldehyde. We have found the mystery molecule I alluded to in the previous video. In summary, the mechanism for hydroboration-oxidation of internal alkynes is the same as that for internal alkenes. Of course, the initial result is an enol, which quickly rearranges into a ketone. We would expect symmetrical alkynes to produce 1 ketone, but asymmetrical alkynes to potentially produce 2 ketones. For terminal alkynes, dicyamyl borane or other reagent like 9BBN is used to ensure the enol is formed. The OH group lands on the primary carbon at the end of the chain. When it rearranges, it becomes an aldehyde. Coming up, it is time for the halogens. Thank you very much for watching. If you enjoyed this video, please like and subscribe as I have more in development. To prepare for the upcoming alkynes and halogen video, I suggest watching the one with the alkenes.